how Voyager 1 still reaches Earth on just 22 watts on November 14th, 2023, while most of the world was scrolling through their phones and going about an ordinary Tuesday, a machine 15 billion miles from Earth suddenly stopped making sense. Voyager 1, the farthest human-made object in existence, was still transmitting. Its radio was still on, its power was still flowing. But the data arriving at Earth was pure gibberish, an endless repeating pattern of meaningless ones and zeros. Not silence, not static, nonsense. And here's the part that should be impossible. The engineers assigned to fix it could not see the spacecraft, could not touch it. And every single command they sent would take 22.5 hours just to arrive. This is the story of how a 46-year-old machine running on the power of a refrigerator light bulb still whispers to Earth from interstellar space, and why that whisper might matter for finding life beyond our solar system. Before we go any further, if you love stories about humanity reaching into the dark and finding answers, hit subscribe. This channel is built for people like you, and you do not want to miss what is coming next. Now let's talk about that light bulb. Because most people, when they hear that Voyager 1 is still in contact with Earth, assume it must be carrying some enormous, powerful transmitter. Something industrial. Something built like a broadcast tower. The truth is almost absurd. The radio transmitter on Voyager 1 broadcasts at roughly 22 watts. That is less power than the bulb inside your refrigerator. It is about the same as the little reading lamp on a nightstand. And that faint 22-watt signal has to cross more than 15 billion miles of empty space before it reaches us. Think about what happens to a signal over that kind of distance. Radio waves spread out as they travel, like ripples on a pond, and their strength drops with the square of the distance. Double the distance, and the signal becomes 4 times weaker. Now stretch that across 15 billion miles. By the time Voyager's transmission arrives at Earth, the signal has faded to about 1/10 of a billionth of a trillionth of a watt. That number is so small it barely means anything to a human brain. So here's a comparison. The power we receive from Voyager 1 is roughly 20 billion times weaker than the power it takes to run a digital watch. A watch. The thing you forget you are even wearing. And yet, engineers in California read that signal every single day. They decode it, they extract science data from it, and they send commands back. Which raises the obvious question: how is that even possible? The answer starts on the ground with some of the largest machines humanity has ever pointed at the sky. NASA operates a network called the Deep Space Network, 3 giant antenna complexes spaced around the planet in California, Spain, and Australia, so that no matter how the Earth rotates, at least one station can always see deep space. The crown jewels of this network are dish antennas 70 meters across. That is a single antenna wider than a football field. A curved bowl of metal the size of a small stadium built to catch whispers. These dishes work like enormous hearing aids. They collect Voyager's incoming radio waves across their entire massive surface and focus every bit of that energy down to a single point, where receivers cooled to just a few degrees above absolute zero amplify it without drowning it in their own electronic noise. Because that is the real enemy at these power levels. Noise. The universe hisses. Electronics hiss. Even the warmth of the antenna itself generates interference. Pulling Voyager's signal out of that hiss is like standing in a roaring stadium and trying to hear one specific person on the far side turning a page in a book. And even after all of that hardware does its job, the data crawls. In its prime, Voyager could send images at tens of thousands of bits per second. Today, its science data trickles home at 160 bits per second. At that rate, downloading a single song would take days. The engineers do not care. They are not downloading songs. They are downloading the only first-hand measurements of interstellar space that humanity has ever possessed, and 160 bits per second of that is worth more than all the bandwidth on Earth. But the ground stations are only half the miracle. The other half was built into the spacecraft itself, back when disco was on the radio and the first Star Wars film was still in theaters. Voyager 1 launched on September 5th, 1977, and the engineers who designed it faced a brutal reality. There would be no repairs, no upgrades, no second chances. whatever they bolted onto that spacecraft had to work alone for decades in an environment colder than anything on Earth, flooded with radiation, and eventually so far from the sun that solar panels would be completely useless. That last problem forced one of the most important decisions of the entire mission. Beyond Jupiter, sunlight becomes too weak to power a spacecraft, so Voyager does not use solar panels at all. Instead, it carries 3 radioisotope thermoelectric generators, devices that hold pellets of plutonium-238. The plutonium is not burned, and it is not part of a reactor. It simply decays naturally and constantly, and that decay releases heat. Thermocouples convert the heat directly into electricity with no moving parts, nothing to jam, nothing to wear out. At launch, those generators produced about 470 watts. But radioactive decay follows a strict schedule. Plutonium-238 has a half-life of about 88 years, which means the power supply fades by roughly 4 watts every single year, like a battery draining in slow motion across half a century. Today, Voyager 1 has barely half its original power left, and the number drops every day. The engineers cannot stop it. They can only manage it. And the way they manage it has become one of the most fascinating survival stories in the history of engineering. Over the years, the team has switched off instrument after instrument, heater after heater, choosing again and again what the spacecraft can live without. They turned off the cameras in 1990. They shut down heaters that were supposed to keep the science instruments alive, fully expecting those instruments to freeze and die. And then something remarkable happened. Several of them just kept working, operating at temperatures far below anything they were ever tested for, decades past their design lifetime. Nobody at NASA can fully explain it. The machines simply refuse to quit. The computers tell the same story. Voyager 1 runs on 3 computers with a combined memory of about 69 kilobytes. The phone in your pocket has millions of times more. Voyager's entire brain could not store a single photo from a modern camera. It processes commands using technology from the early 1970s, and it records its science data on an 8-track tape recorder. And this ancient, tiny, fading machine is the only object humanity has ever sent into the space between the stars that still talks to us. To understand how it got there, you have to go back to a discovery that almost nobody noticed at the time. In 1965, a graduate student and aerospace engineer named Gary Flandreau was doing summer work at NASA's Jet Propulsion Laboratory when he noticed something buried in the orbital mechanics. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would all drift into a rare alignment, arranged like stepping stones on the same side of the sun. A spacecraft launched at just the right moment could use the gravity of each planet as a slingshot, stealing a little momentum from each one, accelerating and bending its path toward the next. This alignment happens once every 176 years. The last time it occurred, Thomas Jefferson was alive. Miss the window, and no one born in the 20th century would ever get another chance. NASA did not miss it. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, and what it saw rewrote the textbooks. It found erupting volcanoes on Jupiter's moon, Io, the first active volcanoes ever seen beyond Earth. It revealed that Saturn's rings were not smooth bands, but thousands of intricate braided ringlets. And it stared into the thick orange haze of Titan, Saturn's largest moon, and found a world with a dense nitrogen atmosphere, the only moon in the solar system that has one. That single flyby changed the search for life forever, because Titan turned out to be a frozen laboratory of organic chemistry, a place where the ingredients of biology are being assembled right now. Decades later, NASA is sending a mission called Dragonfly to fly through Titan's skies, and the reason we care about that moon at all traces directly back to Voyager 1. The Titan flyby came with a price, though. To get that close look, Voyager 1 had to dive beneath Saturn's south pole, and Saturn's gravity threw it upward, out of the plane of the planets entirely. There would be no visit to Uranus or Neptune for Voyager 1. Its planetary mission was over. From that moment on, it had exactly one destination left: the edge of everything. But before it left, it turned around. On February 14, 1990, at the request of the astronomer Carl Sagan, Voyager 1 swung its camera back toward the inner solar system and took one final series of pictures. In one of them, caught inside a stray beam of scattered sunlight, sits a single pale dot, less than 1 pixel wide. That dot is Earth. Every human being who has ever lived, every war, every love story, every civilization, contained in a fraction of a pixel photographed from 3.7 billion miles away. Sagan called it the pale blue dot, and it remains perhaps the most humbling photograph ever taken. Shortly afterward, the cameras were switched off forever to save power. Voyager 1 has been flying blind ever since, navigating by radio alone into territory no machine had ever entered. That territory has a boundary, and crossing it was the discovery of a lifetime. The sun constantly blasts out a stream of charged particles called the solar wind, which inflates a gigantic protective bubble around the entire solar system. Scientists call this bubble the heliosphere. Inside it, we live in the sun's weather. Outside it lies the interstellar medium, the thin soup of gas, dust, and cosmic radiation that fills the space between the stars. For decades, nobody knew exactly where the bubble ended. The models disagreed. The estimates kept moving. Voyager began feeling the edge long before it crossed it. In 2004, the spacecraft passed through the termination shock, the region where the solar wind slams into interstellar pressure and abruptly slows from supersonic speed to a crawl like river rapids hitting a deep, still pool. For the next 8 years, it pushed through a strange, turbulent borderland where the sun's influence sputtered and faded, and mission scientists argued constantly about how much farther the boundary could possibly be. Then, on August 25, 2012, Voyager 1's instruments recorded something extraordinary. The solar particles around the spacecraft suddenly dropped away almost to nothing, while galactic cosmic rays surged. Months later, an eruption from the sun made the plasma around Voyager ring like a struck bell, and the tone of that ringing revealed the density of the surrounding material. It was 40 times denser than the solar wind. There was only one explanation. Voyager 1 had left the bubble. For the first time in history, something built by human hands was swimming in the matter between the stars. Now hold on to that thought, because it is exactly why this old spacecraft still matters for the search for life. Every star system in our galaxy sits inside the interstellar medium, the way islands sit inside an ocean. Cosmic radiation from that ocean crashes against the protective bubbles of other stars, and how much of it gets through helps decide whether the planets inside are gentle harbors or sterilized wastelands. Radiation strips atmospheres. It shreds complex molecules. It can slowly ruin a world that would otherwise be habitable. When scientists today model whether a planet around another star could support life, they need to know what interstellar space is actually made of, how dense it is, how its magnetic fields twist, how hard its radiation hits. And the only direct measurements ever taken from inside that ocean come from 2 aging spacecraft, and Voyager 1 was first. It is not just leaving the solar system, it is sampling the very environment that decides which worlds get to be alive. There is a second gift hiding in that data too. Voyager discovered that the boundary of our bubble is not a clean wall, but a messy, foaming frontier, and that some interstellar radiation leaks deeper into the solar system than the old models predicted. That single fact now feeds into how scientists judge the habitable zones of other stars. A red dwarf with a weak protective bubble might bathe its planets in galactic radiation, even when they sit at the perfect distance for liquid water. In other words, a 1970s spacecraft with an 8-track recorder is quietly helping decide which of the thousands of newly discovered exoplanets deserve humanity's closest attention. Which brings us back to that Tuesday in November of 2023 when the whisper turned to gibberish. The telemetry arriving at Earth had collapsed into a repeating, meaningless pattern. The engineers could tell the spacecraft was alive. The carrier signal was still there, still steady, like a heartbeat with no voice. But every attempt to read its data failed. And the team at the Jet Propulsion Laboratory faced a repair job unlike anything else in engineering. The patient was 15 billion miles away. A command sent from Earth took 22.5 hours to arrive, and any response took another 22.5 hours to come back. Ask a question on Monday morning, and the answer arrives Wednesday. One question, 2 days. Every guess, every test, every experiment ran on that unforgiving clock. There was another problem, and it was very human. The people who designed Voyager's computers had largely retired or passed away. The documentation was spread across decades of old reports, some of it existing only on paper in boxes, written in the engineering dialect of the 1970s. The team had to become part detective, part archaeologist, digging through half-century-old schematics to relearn how their own spacecraft thought. For months, they worked the problem. And in March of 2024, they tried something clever. They sent a command nicknamed a poke, an instruction that nudged the flight data system into trying different sections of its own software, hoping the response would reveal where the corruption lived. 2 days later, the answer came back, and buried inside, it was a readout of the computer's entire memory. Now they could compare. Somewhere in that memory map was the wound. They found it. A single chip in the flight data system had died, taking about 3% of the computer's memory with it, including code the spacecraft needed to package its data for transmission. The chip could never be repaired, so the team did the only thing left. They performed surgery on the software of a 46-year-old computer from 15 billion miles away. They carved the lost code into pieces, rewrote it, and tucked the fragments into scattered leftover corners of the remaining healthy memory, updating every reference so the ancient processor could still find its own instructions. Remember, this entire computer holds 69 kilobytes. There was no room for error, barely room for the code itself. On April 18, 2024, they transmitted the first relocated section, the part responsible for reporting the spacecraft's health. Then they waited through the 45-hour round trip, knowing that if they had miscalculated by a single memory address, they might never hear a meaningful word from Voyager 1 again. On April 20th, the signal arrived. Clean, structured, readable engineering data. After 5 months of gibberish, Voyager 1 was speaking clearly again. The room at JPL erupted. Engineers who had spent their entire careers on this mission were openly emotional. Weeks later, the science instruments came back online too, and the spacecraft resumed its quiet reporting from the space between the stars as if nothing had happened. And the rescues have not stopped. In 2024 and 2025, the team kept performing miracles of rationing, switching between thrusters as fuel lines slowly clogged with residue, reviving backup thrusters that had not fired in over 2 decades, and shutting down more instruments to stretch the fading plutonium a little further. At one point, engineers successfully commanded thrusters back to life, while the giant antenna in Canberra, the only dish on Earth powerful enough to send Voyager commands, was about to go offline for upgrades. If the thruster fix had failed, the spacecraft could have drifted out of alignment with Earth before anyone could correct it, and the signal would have been lost, possibly forever. It worked. Of course it worked. This spacecraft simply does not know how to die. The rationing has reached levels that sound almost like folklore. In early 2025, the team shut down the cosmic ray instrument that had been central to detecting the crossing into interstellar space, sacrificing one of the mission's crown jewels to buy the others a little more time. Engineers now measure the remaining lifetime of the mission in single watts, weighing each instrument against the others like a family deciding which room of the house they can still afford to heat. But it will. And everyone on the team knows it. The power drops by about 4 watts a year, and no amount of clever rationing can change the physics of radioactive decay. Sometime in the early 2030s, most likely, there will no longer be enough electricity to run even a single instrument and the transmitter at the same time. One day, one of those 70-meter dishes will listen at the appointed hour, and there will be nothing there. No failure, no explosion, no drama. Just a whisper that finally fades below the noise, somewhere past 15 billion miles. The team already has a quiet name for that day. They simply call it the mission's long goodbye. Here is the strange and beautiful part, though. That will not be the end of Voyager 1. It will be the beginning of its longest chapter. Because bolted to the side of the spacecraft is a golden phonograph record, and it might be the most optimistic object our species has ever created. Carl Sagan led the team that made it, and they filled it with the sound of Earth. Greetings in 55 languages, the music of Bach, Beethoven, and Chuck Berry. A heartbeat, laughter, the sound of rain, of surf, of a mother speaking to her child. There are 115 images encoded on it, showing what we look like, how we live, where we are. The record comes with instructions drawn in the universal language of physics, and a piece of uranium whose steady decay works as a clock so that anyone who finds it can calculate how long it has been traveling. Hidden inside the collection is one recording more intimate than all the rest, the brainwaves of a young woman newly in love, captured while she thought about the history of the world and the man she was going to marry. We sent our science to the stars, but we also sent a beating heart. The record was built to last more than 1 billion years in the vacuum of space. Let that timescale sink in. 1 billion years ago, the most complex life on Earth was algae. 1 billion years from now, the sun will have changed so much that Earth itself may no longer be habitable. And through all of it, Voyager 1 will still be out there, silent and cold, carrying Chuck Berry past the stars. In about 40,000 years, it will drift within about 1.6 light-years of a small red star called Gliese 445. It will not stop. It will never stop. It will simply keep falling around the center of the Milky Way, completing an orbit of the galaxy every 225 million years, outlasting the pyramids, outlasting the continents in their current shapes, very possibly outlasting humanity itself. If any other civilization ever plucks it from the dark, they will find our music, our faces, and our address, sent by a species that could barely leave its own planet, but decided to introduce itself to the galaxy anyway. So when you hear that Voyager 1 still reaches Earth on just 22 watts, understand what that sentence really contains. It contains a rare planetary alignment noticed by a summer student. It contains plutonium quietly bleeding warmth into thermocouples for half a century. It contains antennas the size of stadiums straining to catch a signal 20 billion times fainter than a watch battery. It contains retired engineers, paper schematics, and software surgery performed across a distance light itself needs nearly a full day to cross. And it contains the first direct taste of the interstellar ocean that every living world in this galaxy must swim in, knowledge we will carry with us when we finally go looking for those worlds ourselves. For thousands of years, humans looked at the space between the stars and saw only a void, empty, unreachable, and silent. Voyager 1 went there anyway, and it turns out the void is not silent at all. It hums with plasma, it crackles with radiation, and somewhere inside it, an old machine built by people in bell-bottoms is still doing science on the power of a refrigerator bulb, still calling home every single day, still proving that the distance between impossible and done is mostly a matter of refusing to stop. If this story gave you chills, hit that like button. It genuinely helps more curious people find this video. And subscribe, because next time we are talking about a signal astronomers detected from deep space that repeats on a perfect schedule. And after years of study, nobody can fully explain what is sending it.